Hello there. So a little while ago, I launched this ESP32 development board, which I designed and developed. It's called the ESP32-S3 PowerFeather, and what makes it special is that it has extensive power management and monitoring features. How extensive? Well, right here is a dashboard of some of the power-related things you can monitor and control on the ESP32-S3 PowerFeather. But we'll get to this later. For now, I'd like to tell you that the board is targeted for one, portable battery-powered projects, specifically those powered by lithium-ion or lithium polymer batteries like this, or two, for off-grid remotely deployed projects, still with LiPo or Li-ion batteries, but charged with something like a solar panel. In this video, I'd like to give you a little showcase of the ESP32S3 PowerFeather. I'd like to first do a hardware tour to take you around the board, then do an overview of the power-related features and capabilities, and finally, do some demonstrations to see those features and capabilities in action, which is where this dashboard will come in. Anyways, let's start with the hardware tour. So the first thing to note about the ESP32S3 PowerFeather is that it's in the feather format, which is a format for stackable dev boards and shields from Adafruit. The shields are called feather wings, and an example is this one with an OLED screen and some buttons. Since this board is in the feather format, you can use feather wings like this to add functionality to it. For example, I have here another ESP32S3 PowerFeather. This one has female header soldered on. And what I can do is stack this feather wing on top, like so. And just like that, my PowerFeather now has an OLED display and some buttons that I can play around with. Now, there are a lot of these feather wings from Adafruit, but since the feather format is open, there are also a lot of such modules from other makers, like these ones on Tindi, or even from other companies like these ones from Worth Electronic. This means that you have a wide selection of hardware when building out your prototypes with ESP32S3 PowerFeather. Moving on, we have here a USB-C connector, which accepts a 5-volt power source. The board itself can sync up to 2 amps from that source. This USB-C connector is also routed to the pads of the ESP32S3's native USB peripheral. So not only can you program and communicate with the PowerFeather through USB serial, you can also have it pretend to be a keyboard or a mouse or a flash drive or other USB device classes. Here you have a JSTPH connector where you can plug in your lithium ion or lithium polymer batteries like this one. Just make sure that the battery connector polarity is the same as the one printed on the board still screen. So for example, if the board is oriented this way, then the positive terminal, the one with the red wire, should be on the right, while the negative terminal, the one with the black wire, should be on the left. On the side of the JSTPH connector is a header hole for connecting a thermistor. This thermistor is used for measuring the battery temperature, which in turn is used by the charger IC to decide whether or not to reduce the charging current or even to cut off the charging current. On either side of the USB connector are two LEDs. This red LED is labeled CHG and indicates charger status. Normally it's off, but it will light up if the battery is being charged or blink when something is wrong, like when the battery temperature limits are exceeded. The other is just labeled LED, and it's a green user LED that can be freely used by the application firmware. You also have two buttons. The button labeled RST is used for resetting the ESP32S3, and the other one is labeled BTN, which is a user button. So again, it can be used freely by the application firmware. Here you have a Stemma Qt connector, which is another avenue for adding functionality to the board aside from feather wings. Stemma Qt is a plug-and-play board and sensor connector system, again from Adafruit. I have here a couple of Stemma Qt modules. This one is an analog to digital converter breakout, and this one is another OLED display. Now, the reason it's plug and play is because you don't have to solder anything. You can just connect it like this. Also, since Stemma Qt is actually just an I2C bus, you can daisy chain them like this. So you can imagine extending the chain further and connecting lots of modules onto one connector. Like Featherwings, there's also a wide selection of Stemma Qt modules from Adafruit, from other makers, and other companies, like the ones on this list or Onsemi. Oh, and one more thing. PowerFeather can enable or disable power to the modules connected to the Stemma Qt connector. This is, of course, very useful for power saving. For example, if you don't need these two modules, you can just turn off the Stemma Qt connector power output and then restore the power to these modules when needed. On either side of the board, you have two 16-pin headers. Most of them are signals routed to the ESP32-S3, 24 to be specific. Of that 24, 23 are general purpose input-output, so think analog, digital, or peripheral signals, and one is reset. So you can reset the ESP32-S3 either by pressing the reset button or by pulling this reset pin low. The rest of the header pins are power related. So you have two ground pins here and here. You also have another power input that can take up to 18 volts called VDC here. Now, similar to the USB-C connector, the board can sync up to 2 amps from power sources connected to this input. This is where you'll connect an external DC adapter or a solar panel. There is VS, which outputs either the power source from USB or the VDC pin. So if there's only USB power, then that appears on VS. If only VDC power is present, then that appears on VS. If both power sources are present, then whichever has the higher voltage wins, and the winner appears on VS. If neither USB power or VDC power is connected, then there's no output on VS, even if there's a battery connected. The VS pin can source up to 2 amps. The opposite of that is the VBAT pin, which always has power output as long as one of the USB, VDC, or battery is connected. If there's a battery connected but not USB or VDC power, then VBAT is powered from the battery. If there's a battery connected but a USB or VDC source, or both, is also connected, then VBAT is powered from that source and not from the battery. However, in that case, VBAT voltage will be similar to the battery voltage and not the USB or VDC voltage. So VBAT never goes above 4.2 volts because that's also the maximum battery voltage. VBAT can source up to 3 amps continuous or up to 6 amps in short bursts. It's important to note that VBAT is the input to the 3.3 volt regulator on board. Right beside the VBAT pin is the EN or enable pin. This enables or disables connected feather wings. So in our earlier example, you can turn off this OLED feather wing by pulling the N pin low. There's a 3.3 volt output on this header pin, which also can be enabled or disabled. Again, useful for power saving because you can turn off loads powered from this pin. There's also a special pin called Q on, and it's used for exiting a power state called ship mode, which I'll be demonstrating later. For now though, let's move on to the components on the board itself. You of course have the ESP32-S3, which is the brains of the board. It has a dual-core 32-bit processor that can run up to 240 megahertz. The module used here specifically has 8 megabytes of flash and 2 megabytes of PS RAM. And of course, it has 2.4 gigahertz Wi-Fi and Bluetooth Low Energy 5. The charger IC used is a Texas Instruments BQ25628E. And there's also an onboard battery fuel gauge, which is an Onsemi LC709204F. Together, these two chips are used for implementing the bulk of the power management and monitoring features of the board, which we'll get to later. The 3.3 volt regulator is a Torex Semiconductor XC6220. This 3.3 volt regulator can sustain up to 1 amp and is shared between the board, the 3.3 volt header pin, and the STEMMA QT 3.3 volt header output. So that's it for the hardware tour of the ESP32-S3 PowerFeather. As you might have noticed, even though the board is small and compact, it has a lot going on. So let's now move on to the overview of its features and capabilities. So I think the best way to put into context what the ESP32-S3 PowerFeather is capable of is to show you the multiple hardware it takes to somewhat match its feature set. And I have such a set of hardware here, so let's go over them one by one. The first is a dev board with a low quiescent or deep sleep current, such as this Fire Beetle 2 from DF Robot. For this Fire Beetle, I measured the deep sleep current myself with a Nordic Power Profiler Kit 2, and I was able to verify that it gets down to under 20 microamps. You can also connect a lithium ion or lithium polymer battery to this board and charge it from USB power. Next is a solar power manager or battery charger like this one from Wayshare. Now, you might ask, didn't I mention that the Fire Beetle 2 already has battery charging? Why the need for this one then? Well, the thing is, the Fire Beetle 2 can only charge up to 500 milliamps max and from a 5 volt power source, whereas this one can charge up to 1 amp from USB or with a source up to 24 volts, and that includes solar. But more than that, even if you use a 5 volt solar panel with the Fire Beetle 2, it doesn't charge as efficiently from solar as this one. And the reason is that with this Waveshare Solar Power Manager, you can set the max power point or MPP voltage to maintain, and that is done through the switches at the back. It's advertised as MPPT, but it's not exactly true MPPT. How it works is the solar panels usually specify an MPP voltage, and you set that corresponding voltage in the switches here. So like this panel, for example, it specifies the max power point voltage at 12 volts. So you have to set 12 volts at the back here. Now, the difference of this between a true MPPT charger is with a true MPPT charger, you don't have to set this at all. It would find the maximum power point itself and also keep track of it while it varies a little bit with factors such as illumination and temperature. Now, even though this is not true MPPT, it's still quite effective and provides near MPPT performance, certainly better than solar charging with the Fire Beetle alone. Next is a fuel gauge breakout module. This one is from Adafruit and has the LC709204F. which is an older version of the LC709204F in the PowerFeather. A fuel gauge allows you to get more accurate estimates of battery percent charge more than measuring voltage through a voltage divider and mapping out those voltages to charge levels, especially considering battery loading or temperature. Suffice it to say that there's a reason they don't use voltage dividers for measuring battery percent charge on consumer devices like smartphones, tablets, or laptops. They use battery fuel gauges like this one. And lastly, you have current measurement modules like these INA219 from DF Robot. There are two because one is for battery current measurement and one is for the supply current measurement. Now, I'd like to reiterate the point of showing you these modules, which is it takes all of these to achieve an almost similar set of capabilities as this. I say almost because even with this combination, in terms of features, the PowerFeather still comes out on top. And I created a comparison table to show you what I mean. The first column is for the list of power management and monitoring features, and the other two are for comparing the ESP32-S3 PowerFeather and this set of hardware with regards to those features in the first column. Now, I'm going to be referring to this set of hardware, the Fire Beetle 2, the Waveshare Solar Power Manager, Adafruit LC709203F, and the two DF Robot INA219 as the combination for the rest of the video since it's very long. So let's get into this comparison table. First off is the deep sleep current. For the ESP32-S3 PowerFeather, the deep sleep current is under 20 microamps, while for the combination, it's in the milliamp range. Now, you might ask, didn't I mention that the Fire Beetle 2 has low deep sleep current under 20 microamps as well? And the answer to that is the combination as a whole consumes a lot more current. There are a lot of unnecessary and redundant circuitries in this combination. For example, the Fire Beetle 2 has a charger IC, but because it's not very good for solar, we had to get a Waveshare Solar Power Manager, which also has a charger IC. So that's one redundancy right there. Another example, the Solar Power Manager has a bunch of LEDs for showing the rough battery level. Let me show that by connecting a battery real quick. This, of course, consumes current whether you use it or not. For example, in cases where people are not going to be able to look at it anyways because the device is mounted high up. Plus, it's not very precise because it only tells you the charge in 25% increments because there are only 4 LEDs. Better to use the fuel gauge to measure the battery charge percent and just transmit the values somewhere using Wi-Fi or Bluetooth or display it on a connected display. The point is, the tight integration in the PowerFeather results in lower quiescent or deep sleep current overall, so it wins here. Next is the max input voltage on which the combination wins. The combination can accept up to 24 volts, while the ESP32S3 PowerFeather can only accept up to 18 volts. However, the ESP32S3 PowerFeather wins when it comes to the max charging current, able to charge a battery up to 2 amps versus the 1 amp on the combination. The next feature is the MPP voltage adjustment. We already mentioned that for the combination, specifically the Solar Power Manager. Let me just turn it off real quick. You do this through the switches at the back, but only at specific voltages. So 6 volts, 9 volts, 12 volts, 18 volts, and 24 volts. While for PowerFeather, you can adjust the MPP voltage in the application firmware anywhere from 4.6 to 16.8 volts. I deem this a tie since while the PowerFeather is more flexible, the MPP voltage for the combination can be set up to 24 volts. With regards to adjusting the maximum charging current, however, PowerFeather wins. And that's because it's firmware adjustable for PowerFeather, while for the combination, it's fixed with a resistor. So you have to desolder that and solder a new resistor if you want to change the max charging current. And that's important because the recommended and safe max charging current is related to the battery capacity. For example, for a 500 milliamp hour battery, it's recommended to not exceed a charging current of 500 milliamps. With PowerFeather, you can adjust the maximum charging current to 500 milliamps out of the 2 amps it can do. With the combination, it's fixed to pushing 1 amp, which is okay for a 1000 milliamp hour or larger battery, but pushing 1 amp to our 500 milliamp hour battery is a little bit unsafe. So PowerFeather wins here because of that flexibility. When it comes to enabling or disabling charging, you can do that on the PowerFeather, but not on the combination. And this is useful, for example, if you want to charge below the full capacity, say maybe only up to 80% in order to extend the life of your lithium ion or lithium polymer battery. So again, a win for PowerFeather. Next is the 3.3 volt output. Both have regulators that can output 1 amp, although I would have to give the slight win to the combination, since in the case of PowerFeather, that 1 amp is shared between the components on the board and the stemma QT connector output and the 3.3 volt header pin output. But if you want to disable the 3.3 volt output for power saving, then PowerFeather wins here. On the combination, you can't do that. Next is the 5 volt output, of which the PowerFeather has none. So the combination handily wins in this feature, and it's able to output 1 amp. The next 4 features are related to voltage and current monitoring of both the supply and the battery, and both the PowerFeather and the combination has them. So it's a tie for all 4 of them. Both the PowerFeather and the combination also has state of charge estimation. So again, a tie. What the combination doesn't have is state of health estimation and cycle count estimation, which is helpful to get an idea on how much the battery has degraded over time and if maybe it's time to replace the battery. The combination also doesn't have battery time left estimate. This is a time until the battery is full when charging or until the battery is empty when discharging. So for these 3, the PowerFeather wins. Both of them have a way to connect a thermistor to measure the battery temperature. So it's a tie there. But only PowerFeather has the capability to reduce the charging current based on the battery temperature, or even fully turn off charging if it gets cold enough or hot enough. The last feature are additional low power states on the PowerFeather called ship mode and shutdown mode. In these modes, the battery is electronically disconnected from the board, even if it's physically connected. As a result, the current draw from the battery is very low, under 2 microamps. It can be used when the device is being transported or stored for a very long time with a connected battery. Another use is for off-grid solar power projects. This can be a way to quote unquote turn off the device when the battery level is low, say maybe under 10%. This enables the device to survive long periods without sun And when the sun does come out, it can just turn itself on, start charging, and resume operating. The combination does not have this feature, so PowerFeather wins in this regard. Finally, we come to the price. You might think that because the combination has less power management and monitoring features than the ESP32-S3 PowerFeather, it would be cheaper. But no, if you add up all the prices, the combination totals 38.64 USD at the time of this recording versus the PowerFeather's 30 USD. A small footnote here is that if you remember, one of the features that the combination has but the PowerFeather does not have is the 5-volt output. Well, if you really need 5-volt output, then you can add a DF Robot DC-DC boost module for around 4 USD. But even with that additional module, the ESP32-S3 PowerFeather still comes out cheaper. The catch is that it's only 600 milliamps. The combination can output 1 amp, so it's a little bit of a wash. So in conclusion, if you're building a battery and or solar power project, you can get more for less with the ESP32-S3 PowerFeather, depending on what you need, versus cobbling together multiple modules. By the way, the link for the spreadsheet with this table is in the description if you want to take a look at it yourself. Anyways, we now move on to the demonstrations of the features in this table. Before we get into the demonstrations, let me first give you an idea of the general setup. The ESP32-S3 PowerFeather has Wi-Fi turned on and is acting as an access point. And this tablet is connected to that access point. Let me show you that real quick. The access point's SSID is called PowerFeather Demo. The tablet then loads a web app which is served from the ESP32-S3 PowerFeather. The PowerFeather, of course, being the access point, has the IP address 192.168.1.1. This web app is a dashboard showing power-related telemetry data and controls. Here, for example, is the battery information, such as the voltage, current, charge level, time to full or time to empty estimate, although this one is still being estimated, battery health, and battery cycle counts. You also have supply information, such as the voltage and current. Here you have controls related to charging. For example, you can enable or disable charging using this switch and set the max charging current using this slider. This slider is in milliamps and goes all the way up to 2000 milliamps or 2 amps. But right now it's set to 50 because that's the minimum. This displays the battery temperature if you have the battery temperature sense enabled through the switch. Here are switches for turning on or off the board's 3.3 volt outputs independently. This one is for the header pin 3.3 volt output, and this one is for the stem QT 3.3 volt output. You have another slider, this time for setting the max power point or MPP voltage of the solar panel. This slider is in millivolts and goes all the way up to 16,800 millivolts or 16.8 volts. Although right now it's set to 4,600 millivolts because that's the minimum. And finally, you have buttons for entering low power states, ship mode, and deep sleep. All of these are implemented using the PowerFeather SDK, which is an open source library for accessing the ESP32-S3 PowerFeather's power monitoring and power management features. It's available in the Arduino library registry, as well as in the ESP IDF component registry. So you can create your PowerFeather applications either using Arduino or ESP IDF. By the way, The entire code for the web app is available on GitHub if you want to try it out on your PowerFeather yourself. Link is in the description. Anyways, let's now move on to the demonstrations. The first demonstration shows the board's power inputs, which is the battery, USB, and VDC pin. For this demo, I'll be using a PowerFeather Proto Wing, which breaks out the VDC pin into a barrel connector. You can see that the ESP32-S3 PowerFeather is already stacked on top of the Proto Wing like so. So with this, I can connect more easily an external DC source with a barrel plug like this one. But for now, the only power source I have connected to the board is the battery. The dashboard tells me that the battery voltage is at 3.91 volts and the battery current is around negative 100 milliamps. The negative sign indicates that the battery is discharging, which makes sense since it's supplying power to the board, given that there is no USB power or external DC source connected, as indicated by the 0 volt and 0 amp on the supply information display. Now, I'll connect USB power. Notice that the supply information now displays around 5 volts and the current is around 70 milliamps and the battery current is at 0 amps. This means that the battery is no longer supplying the board, but rather the USB power is. Furthermore, the 0 amp battery current indicates that the battery is not charging either, which also makes sense since charging is currently disabled. We'll enable this in a later demo. For now though, it just sits there, neither charging nor discharging. However, if I remove the USB power, the battery immediately takes over and begins supplying the board once again. The supply current goes to 0 and the supply voltage also goes down to 0, albeit more slowly because of the input capacitors. Anyways, the point is there was no brownout reset caused by the USB power removal. The web app stayed connected through all of that. Now, let me just connect USB power once again. Now, I'll plug in an external DC source through the barrel connector. This one is at 18 volts, which should be reflected in the dashboard. Here you go, around 18 volts, 17 point something volts more specifically. And the current is now at 20 milliamps. Now, you'll notice that this current is smaller than before. Let me just unplug it again so you could see it goes back to around 5 volts and around 70, 80 milliamps. And if I plug it back again, around 18 volts and 20 milliamps. Now, the reason for this is because the charger used in the PowerFeather has a switching topology, which is more efficient than the linear chargers used in other boards. So instead of dissipating that extra voltage as heat, it's used to deliver the same power but at a lower current, which you can now see here. On another note, as you can see, it's perfectly okay to have all 3 power sources connected at the same time, so battery, USB, and external DC source. The board will juggle all these sources automatically, so even if you continuously plug in or remove power sources, as long as one of the 3 is connected at any point in time, the board will stay powered without brownout reset. So that's it for the first demonstration. In this demonstration, I'll be showing you the current consumption of the board in 2 low power states, deep sleep and ship mode. Let me first describe the overall setup real quick since I'll be switching to a screencast of my desktop later. First off, instead of a battery, I'll be using a Nordic Power Profiler Kit 2. to supply the board and to measure the current consumption. When I press this button on the dashboard, the board will enter ship mode. Again, ship mode is a power state that electronically disconnects the battery, in this case, the Nordic Power Profiler Kit 2, even if it's physically connected. As for exiting ship mode, there are two ways. One is to connect a power source either through USB or an external DC source through the VDC pin. Or second is to pull a pin called Q on low for around 1 second. I'll be using the latter, hence this button connected between Q on and ground. So when I press this button, Q on will be pulled low. When I press this other button on the dashboard, the ESP32-S3 will enter deep sleep. And to exit that deep sleep, I'll just press the reset button. Anyways, let me now switch to my desktop for the Nordic Power Profiler Kit 2 software. And there you go. I am now in the Nordic Power Profiler Kit software. I set the supplied voltage to 3700 millivolts or 3.7 volts, which is the nominal voltage for lithium ion and lithium polymer batteries. So I'm going to start the current measurements now. With the board acting as an access point and serving this web app to the tablet, the board is consuming around 100 milliamps of current. I'm going to enter deep sleep first, and I will press the button on the dashboard now. As you can see, there was a tremendous drop in current consumption right when I pressed the enter deep sleep button. And right now, the current consumption is averaging 20 microamps and going down. It should go under 20 microamps. So yeah, this flow of a current consumption during deep sleep is very cool. Now, with the ESP32-S3 in deep sleep, the tablet lost the connection to the web app. I will now try to wake up the ESP32-S3 using the reset button. Now, the current consumption rose again, and I should be able to reconnect on my tablet afterwards. Hold on, I'll try to connect manually. And there you go. The ESP32-S3 is awake again and serving the web app. Now, let's try entering ship mode. I will press the button now. Again, a tremendous drop in current consumption. Let's see the current consumed in ship mode. And this time, it's much lower, 1.45 microamps, which is what you would expect since the battery is quote-unquote disconnected. To wake up, I'll hold the Q on button for around 1 second. And there you go. The current consumption rose again. And I should be able to reconnect on my tablet. And that's it for the current consumption of the ESP32-S3 PowerFeather in deep sleep and ship mode. For this next demonstration, I'll be showing you one of the ways to save power, and that is by turning off the board's 3.3 volt outputs. To do that, I have connected an LED to the 3.3 volt output header pin and ground, and a Stemma QT module with a power LED indicator on the Stemma QT connector. Currently, both of these 3.3 volt outputs are enabled, and so both LEDs also light up. But I can just turn them on or off using these switches on the dashboard. So first, for the 3.3 volt output header pin, I'm going to turn it off, on, off, and then back on again. And then for the STEM Acuity module, off, on, off, on. One thing you might notice is that when I disable the STEM Acuity output power like this, the battery information and the supply information seems to go away. It's more noticeable with the battery information than the supply information because we don't actually have a supply connected. But I assure you it also happens to that too. Anyways, this is because the charger and the fuel gauge where these information come from also uses the same I2C bus as the STEMMA QT connector. And so if the STEMMA QT output power is turned off, the charger and the fuel gauge also can't use this I2C bus as well. So if you have disabled the STEMMA QT 3.3 volt output, the workaround is to turn on the STEMMA QT output power momentarily when you want to get battery and supply information. So one more thing, whether these 3.3 volt outputs are enabled or disabled persists through deep sleep. For example, I have them both enabled right now. And if I enter deep sleep by pressing the button on the dashboard, let me just wait until the web app is disconnected to confirm that we are in fact in deep sleep. Okay, so the web app is disconnected so we can be sure that the ESP32 is in deep sleep, but the 3.3 volt outputs remained on. Conversely, if they were disabled before going to deep sleep, they will also have remained disabled. This demonstration is going to be a short one regarding charge controls. Basically, the setup is I have here an ESP32-S3 PowerFeather with a battery connected and stacked on top of a proto wing. I also have an 18 volt external DC source plugged in. So right now, the board is being supplied from the external DC source at around 18 volts and 20 milliamps. There is no current going into the battery because charging is disabled. But once I turn on charging, the charge status LED turns on and the battery current becomes a positive non-zero value indicating that it's charging. It's only at around 40 milliamps, but that's because the max charging current is currently set to 50 milliamps, which is the minimum. If I increase it to say 514 milliamps, the charge current is around 520 milliamps. And I can keep increasing this and the charge current follows suit until I get to the maximum, which is 2000 milliamps or 2 amps, at which point the battery charge current also becomes 2 amps. Now, one important thing to remember here is that you don't have to worry about an overcurrent situation. Remember that this is the max charging current. It's the charging current ceiling. And so the actual charging current might be lower. Either one, because the supply can't actually provide the current, or two, if the charging phase is towards the end, where the charging current is tapered off as the battery approaches full capacity. It just so happens that in this particular case, the external DC source I'm using is a fairly beefy one, able to provide currents more than 2 amps, and the battery is only at 46%, far from a full charge. And so the charger IC determines that it's able to charge safely at the limit I set, which is 2000 milliamps. So this next demonstration is for what I think is one of the most important features of the ESP32-S3 PowerFeather, and that is the ability to measure battery temperature and to reduce charging current or even cut off charging current based on that measured temperature. So for this demonstration, I'll be using an ESP32-S3 PowerFeather with the battery connected and USB power plugged in. Now, measuring the battery temperature is normally done through a thermistor connected to a lone header pin right next to the battery connector, which is this one. But for this demonstration, in order to have more control over the measured battery temperature, I'm going to be using a potentiometer to simulate a thermistor. Next, I have a graph showing the relationship between the battery temperature and the max charging current percent. This max charging current is the same one we mentioned in the last demonstration, which is this one. For this demo, I've set the max charging current to around 1000 milliamps just to make the math easier. And this y-axis represents a certain percentage of that 1000 milliamps. So for example, the 40% here means 40% of 1000 milliamps, which is 400 milliamps. I have the battery temperature sense enabled, and I have set the potentiometer such that the measured temperature is initially around 25 degrees Celsius, which is within this temperature range, 15 degrees to 35 degrees Celsius. And this graph tells me that in this temperature range, uh, the battery should be charging at 100% of the max charging current. And if I enable charging, I have that. I have 1 amp or 1000 milliamp uh, battery charging current at 25 degrees Celsius. Now, what if the battery was to get colder, say maybe between 10 and 15 degrees Celsius? Now, let's set the temperature to something within that range using the potentiometer. Okay. Okay, I think that's good enough. So 14, 13 degrees Celsius is between 10 and 15. And the graph tells me that at this temperature range, I should be charging at 40% of the max charging current set, which is what we get here, close enough to the theoretical 400 milliamps in this temperature range. But what if the battery temperature was to get even colder, say maybe 6 or 7 degrees Celsius, between 0 and 10 degrees? So let's do that. Okay, I think that's also good enough. At this temperature range, the graph tells me that I should be charging at 20% of the max charging current set, and that's 200 milliamps. Again, we see that here. And what if we go even lower, below 0 degrees? So I'm going to set that. Okay, so I'm now at negative 0.28 degrees Celsius. And as you can see, the battery current is now 0 amp, which indicates that the battery stopped charging. We also have the charge status LED blinking, which means there's an error. In this case, we know that it's because the battery temperature limit has been exceeded. The battery temperature went below 0 degrees Celsius. But what if we instead go the other way? What if the battery temperature rises because the battery got warmer or hotter? So let's try that. But first, let me go back to this Goldilocks region, the 15 to 35 degrees Celsius region. Okay, I'm now at 27 degrees Celsius, and that's also within this region. And you notice that we're back at 1 amp charging, and the charge status LED has also stopped blinking, meaning everything has returned back to normal. When the battery temperature gets higher or hotter, say maybe 36 to 37 degrees Celsius, right between 35 and 40 degrees Celsius, we expect the current to also be around 400 milliamps. So let's do that. Okay. So now it's at 38.22 degrees Celsius. And just as we expected, the battery charging current is around that as well. Going even hotter, say maybe 45 degrees, between 40 and 50 degrees Celsius. Okay. At 46, so this temperature region should have 20% max battery charging percent. So 200 milliamps. Again, we get that here. Now, what if the battery temperature is above 50 degrees? So let's set that. I overshot, but I think it's good enough. So yeah, like when the temperature was below 0 degrees Celsius, at above 50 degrees Celsius, the battery also stops charging, as well as the stop charge status LED also starts blinking. So that's it for the battery temperature sensing feature of the ESP32-S3 PowerFeather. The last feature I want to demonstrate is the ability to set the max power point voltage, which is important for extracting power from solar panels like this effectively. Now, I'm going to be taking this setup outside, but before I do, I want to describe it to you now, since later the main field I'll be showing you is of the dashboard. So here I have an ESP32S3 PowerFeather with a battery connected and stacked on top of a PowerFeather Proto Wing. This Proto Wing enables me to connect this PowerFeather solar panel more easily using the barrel connector breakout. Now, this is the solar panel that I showed you earlier, the one with the max power point voltage at 12 volts. So that's it for the setup. I will now be taking this outside and I'll be back. Okay, I'm back, and the setup I described earlier is now outside. I'm now sharing my computer screen and I have the dashboard open on a browser. Just to show you that I am controlling the setup remotely, I'll enable charging, which should turn on the red charger status LED. The red charger status LED is currently off for now, but when I enable charging, there you go, it lights up. Anyways, on the dashboard, the max charging current is currently set to 2000 milliamps or 2 amps. And initially, the MPP voltage is set to the minimum, which is 4600 millivolts or 4.6 volts. Which means in this scenario, the charger IC will pull as much current as it can from the solar panel, even if the solar panel voltage collapses below the rated max power point voltage. And you can see just that. The supply voltage is around 4.6 volts, well below the panel's rated MPP voltage of around 12 volts. The supply current is at 0.66 amps. So if we compute power from the solar panel, it's 4.6 volts times 0.66 amps. So let's just switch to the computation spreadsheet. That's 4.6 volts at 0.66 amps. So right now with the MPP not set, we're extracting around 3 watts from the solar panel. Let's also compute the power delivered to the battery. That's 3.77 volts at 0.68 amps. So 3.77 volts at 0.68 amps. So we're delivering around 2.6 watts to the battery with the NPP not set. Now, let's go back to the dashboard and set the max power point voltage to the panel's rated voltage of around 12 volts. So just like that. And what it does is that it tells the charger IC, hey, regulate the current draw from the panel such that the voltage does not go below whatever is set here. And we see that working here. The supply voltage is now maintained at around 12 volts or whatever we set here, 11,728 millivolts or 11.7 volts. And with just that, you can see an obvious jump in the current delivered to the battery. You can actually play around a little with this value. For example, I can set it higher or lower than what the panel spec sheet says to see if we can get even higher currents. So for example, I can set it a little lower to around 10.6 volts, and we can see that's an even bigger jump of current delivered to the battery. So for now, let's compute the supply power. That's 10.68 volts at 0.55 amps. And there you go. We can see a huge jump in the power extracted from the solar panel when we set the MPP voltage. Let's also compute the power delivered to the battery. That's 3.83 volts at 1.3 amps. That's almost 5 watts delivered to the battery with the MPP set. So what we saw here was that when we prevented the solar panel voltage from collapsing by setting the max power point voltage, we extracted more from the solar panel and in turn delivered more power to the battery. And in this case, the power increase was quite significant. I think almost twice as much. So that's the advantage of the ability to set the MPP voltage of the ESP32-S3 PowerFeather. So there you go. That was a little showcase of the ESP32-S3 PowerFeather. Well, actually, it's not very little since it's been a longer video than I expected. But that's just a testament, I think, as to how feature-packed this little board is. Even with all of that, there's more stuff that I didn't get to mention in this video. So if you need more info, you can go to www.powerfeather.dev. It's a landing page where you can find links to the board documentation, socials, and where to buy the board. Anyways, I hope this video has got your gears turning as how you might use ESP32 S3 PowerFeather in your next project. Until next time, bye.